Hello, everybody, and welcome to the series, webinar series designed for CMI and by CMI. I'm Cynthia Howell, and I'm going to be your moderator for today. I'd like to tell you a little bit about the webinar. For those of you that haven't been on, but most of you are very familiar with how we run our webinar series. If you have a suggestion for a future webinar, please make sure that you add that to the exit survey and or email us. This is a public webinar, and a recording is going to be available next week at aimslab.gov/CMI, and note again that it's under the workforce menu. Questions, our presenters today would like for you to hold your questions to the end of the presentation. In the meantime, however, it does take some time to type them in, so I encourage you to queue them up so that when the presentation is over, they are ready to go with questions. I'd like to introduce our team today and of presenters. And first we have Fei Zhou. He has a PhD in physics from MIT, and he has spent some time as postdoc at MIT and also UCLA. And he also worked as an assistant research engineer at UCLA before he joined Lawrence Livermore National Lab as a staff physicist. He has several interests, including computational physics in a range of materials and more. And he is currently working with CMI colleagues on developing and applying machine learning methods for materials design. Joining Fei Zhou today will be Ming Tang. Dr. Tang earned his PhD in materials science and engineering from MIT as well. He began his career at Lawrence Livermore as a postdoc and then as a staff person. He led projects there, and after 4 years with Lawrence Livermore, he moved into the industrial sector and spent some time there with materials and corrosion research at Shell Technology Center in Houston, and also working across several different problems and issues, including materials and corrosion. And now he has formally joined the Department of Materials Science and Nanoengineering at Rice, and he's been there since 2014. I don't want to take any more time of our presenters' time, so if you would mind taking the presentation away here. Fei, thank you.
Hello. Hi, my name is Fei, and I'd like to welcome you today to our webinar. So today I'm talking about machine learning for microstructure data-driven pathway. And one of the original motivation for our work was the CMI breakthrough discovery led by Dr. Orlando Reyes. And Orlando and his team developed advanced aluminum cerium alloys with superior high temperature performance. And with this, they were able to find high volume use of the underutilized cerium, which is a byproduct of higher value, heavier rare earth elements mining. And this helps stabilize the supply chain. Therefore, one of our original goals was to use machine learning to understand the microstructure of aluminum cerium alloys and help alloy development. And more broadly, we like to develop and apply machine learning tools to other CMI projects, such as the modeling of magnets. So, well, the idea of applying machine learning to various disciplines of physical science, including microstructure modeling in material science, is becoming very, very popular, and it's impossible to cover everything, of course. So therefore, we are biased towards presenting some of our own work, as well as showing a few cherry-picked examples of the state of the art of the newest development in this area. So the first subtopic is microstructure image manipulation and generation. So as the first example, Let's look at super resolution. So super resolution means taking a low resolution image. Here we are looking at aluminum cerium micrographs and turn those into high resolution. And as you can see, the left column are the low resolution images. And on the right, you can see the ground truth high resolution graph images. And on the middle are the results of a trained neural network that performs super resolution. And as you can see visually, the super resolution images match the high resolution ground truth very well. And with a tool like this, one will be able to extract detailed and sharp images from low resolution images, which tend to have a larger field of view. And as a second example, we are looking at the effects of processing conditions on the aluminum cerium microstructure images. So if we perform heat treatment on the alloys, the fine microstructures of aluminum cerium tend to become coarser due to heat treatment. And we trained a neural network model on this data set from Orlando's group. And indeed, we were able to correctly reproduce the trends of coarsening of the fine microstructures due to heat treatment. And those examples were 2D images. So let's move on to a sort of state-of-the-art 3D results. So here is the work of Tim Xu, who is a collaborator of mine at Lawrence Livermore. So I'm not on this paper. And what Xu and his co-workers did was to develop a 3-dimensional microstructure generation algorithm using the so-called generative adversarial network. And with this, the model was trained from 3-dimensional data. And you can see that visually, the original input image and the generated complex microstructures were very, very similar, and compare favorably with traditional grain-based generation algorithm called Dream3D. So for more quantitative analysis of Tim's results, look at, for example, the mean particle size distribution and the interface surface area distribution of the original and neural network generated 3D fine microstructures. And they align very well and compare favorably with the results of Dream3D, which is the green distribution. So this is a very impressive work. And so now we have the structures. What do we do? Of course, we are interested in structure-property relationships, which is the central question of material science. The simple application. So here we are looking at X-ray images of aluminum. So this is not exactly microstructures, but I'd like to show you an example of using deep learning to directly help practical applications of alloys and alloy development. So the idea is to use neural networks to train them on X-ray images to find the locations of defects. Here they are pores in the alloy products. So
excuse me, Faye, we're having some technical difficulty with your voice. I wonder if it might help to turn off your video for the rest of the presentation.
Sure, okay.
Let's try that, thanks.
Can you hear me now?
Yes.
Yes.
Okay, so should I go back like a couple of slides?
No, it was just occasional, so you can go
Okay.
forward.
Okay, okay, all right. So so here we trained a neural network on the X-ray images and use that to identify the defects and calculate properties of this alloy, such as porosity density and max pore size. And the results were really good. And application of deep learning on the alloy images has the potential to automate the process of manually identifying the defects and help automate quality control. So let's look at another example. Here, the authors were using three-dimensional neural networks to predict the elastic properties of high contrast composites. And the training data was 3D microstructures, and the data was trained on a neural network with 3D convolutions. And with that, they were able to fairly accurately predict the Young's modulus of these composites. So this is an application where the overall structure, overall property of this complex structure is predicted by a neural network. So, well, if you look at these previous results, right, the data themselves were pixelized or voxelized grid-based data. And a grid-based data sets such as arrays are fairly sensitive to the resolution used and also to the presence of noise. And 3D arrays are fairly memory intensive as well. So to alleviate these problems, I'd like to bring to your attention this emerging direction of graph neural networks. So graph neural networks, or GNN, are neural networks designed to be applied to graph theory. So graph is, of course, not a rigid structured grid-based data, but rather nodes and edges that connect the nodes. And the objective of GNN is to increase the robustness, stability, and discover long-range correlation in these complex structures. So as a real-life example, think about Google. So Google, the initial success of Google back in 1998, around that time, was the PageRank algorithm, which was a graph theory algorithm, not GNN, but a traditional graph theory algorithm that ranks the web pages by looking at how they link to each other. So yeah, so GNN is trying to discover the interconnectedness and figure out how things are correlated. So here's an example of predicting the mechanical properties of materials with complex microstructures. And this complex microstructure consists of grains and the shared grain boundaries. So the grains and grain boundaries form a very complex network. And the interconnectedness is supposed to have profound effects on the material's properties. But in reality, it is hard to quantify these effects because currently available descriptors on the grains are usually limited to isolated quantities, such as the size of the grain, the shape of the grain, or the averaged orientation. And there is no straightforward way to discover long range correlation. And by applying the graph neural networks, the authors convert this grain structure into a graph with the grains as nodes and the grain boundaries as the edges. And they use that to predict the elastic response of the materials very accurately. And as another example, this is graph neural networks applied to magnets. It's a terbium, dysprosium iron alloy. And like the previous example, the grains and grain boundaries were converted to a graph representation. So here, as you can see here, each grain becomes a node in the graph, and they are connected to each other if they share a grain boundary. And the property of these complex microstructures, such as magnetostriction, were fitted to a graph neural network, and they were fairly accurately reproduced. And very interestingly, similar to the PageRank web page ranking of Google, what you can discover is that you can quantify the relative importance of each grain in the microstructure. So here, red grain is a grain that has much more significant effects on the magnetic properties of the system compared to white or blue grain. So such relative importance is essentially impossible to discover without knowing the interconnectedness of individual grains. So yeah, so let's look at the next topic of my talk, which is the prediction of the time evolution of microstructures. So why do we care about the microstructure evolution rules? So in all these previous examples, we were concerned with static images of microstructures. So these microstructures were not correlated. They are looked at one by one. Here we care about the temporal correlation because the kinetics of microstructure evolution by itself is very critical for understanding the formation of microstructures, and knowing the kinetics is important if we want to optimize the microstructures by tuning the processing conditions. And additionally, if we learn the microstructure evolution rules through their temporal correlation, the obtained descriptors can often be reused for structure property relationship predictions via transfer learning. So the temporal correlation helps us understand the static images. And what's more, we have a data problem or data challenge, right? So deep learning is notorious for requiring a very large amount of training data. And by looking at individual images without intercorrelation with them, between them, one often needs to go through this time-consuming process of labeling each image, which takes time and resource. Whereas if we care about the evolution rules, they can be learned autoregressively from either experimental or simulated trajectory, allowing this paradigm of self-supervised learning without manual labeling. So Ming, my colleague Ming, will talk in great detail about this aspect. And here I'd like to show you one simple example of our work in progress, really, recent development. So here we care about learning not only the deterministic driving force of microstructure evolution, but the stochastic fluctuations. So this example is a binary immiscible system, and the free energy surface, as you can see, is a typical double well. And within the miscibility gap, we have an unstable region and a metastable region. Within the unstable region, the phase separation goes through the spinodal decomposition mechanism. And if you only learn the deterministic driving force, we can sort of still reproduce this mechanism. Whereas in the metastable region, the phase separation goes through the nucleation and growth mechanism. And without fluctuations, the system becomes infinitely metastable and nothing happens. Whereas the introduction of proper fluctuations allows the emergence of nucleus, and this system can go through the proper nucleation and growth mechanism. In summary, we have shown you a few select examples, and I'd like to convince you that neural networks offer new capabilities to characterize and manipulate image data, and new algorithms such as graph neural networks allow deeper understanding and mining of complex grain boundary structures. And this data-driven approach, of course, requires a lot of training data, but this can be mitigated by self-supervised learning. And in the future, we would like to achieve even closer integration with experimental effort and provide more quantitative feedback to experiments. And in the long term, I think we can even dream of a future where the data-driven approach and machine learning algorithms can help in every aspect of the materials modeling pipeline, starting from potential fitting to learning the microstructure evolution rules, to performing the microstructure evolution simulations, to discovering structure property relationships. So finally, acknowledgement. We are grateful for CMI for supporting our project 4.1.12, and I'd like to thank our collaborators and in this project, and Ming for his collaboration, and he will give the next presentation. Thank you very much. Ming, would you take over?
Oh, good afternoon. My name is Ming. I'm from Rice University. Very glad to be with you in this CMI seminar. So I'd like to follow on what Fei just talked about and presented a recent work we did together with Fei on extending the machine learning algorithm to predicting microstructure evolution phenomenon in material systems, which is the last topic Fei covered. And here I want to present a little bit more details on this application. And this is based on a new work that's coming out, I believe, tomorrow. Right, so I think we already saved me a lot of time and give a very good introduction and motivation on the application of machine learning to tackle different kinds of microstructure problems. And in the last several years, we have seen very exciting progress and results from such applications. So the machine learning algorithm have been used to classify microstructure, do image segmentation very efficiently to predict the relation between microstructure and property, and also used to optimize the microstructure to do microstructure design. And Fei already gave very nice examples on these applications. So for these applications, we deal with static microstructure images. And the problem we try to tackle next is somewhat more challenging because we want to predict the microstructure evolution, and this requires to deal with imaging sequences instead of static images. We know traditionally microstructure evolution simulations are mainly achieved by solving partial differential equations, for example, in phase field simulations. And so you first derive the governing equations based on the physical principles for certain microstructure phenomena, and then you solve the equations to track the spatial temporal evolution of the structure in the systems. And what we try to do here is to use a machine learning technique, mainly based on the convolutional recurrent neural network, to learn from the PDE-based simulation data, and then replace the PD-based simulations to make the microstructure evolution predictions with high efficiency, and also allows us to make prediction even when the material properties for the system are not completely known. Right? And I'll show you what this means. Right, so, but let me first give a very brief introduction on the machine learning technique we use in this work. Right. So we know the recurrent neural network has been around for quite a while. It is a very natural choice for learning sequential data, such as in language translation, speech recognition, stock market prediction. Right. So in a recurrent neural net, what you do is you provide input to a neural net to generate output, and then you feed this output again as the input to the same neural net to generate a second output. And you can repeat this process again and again to make a sequence of predictions on how the system states will evolve. Right? This could be over time, right? Or over frequency. And this has been used in many different applications. But between the original recurrent neural network model and the technique we use for this work, well, actually there has been a lot of development in between. So one well-known problem associated with the original RNN model is the so-called vanishing gradient problem, which makes it very difficult to train the RNN to see the long-term correlation of the data. Right? And this problem was effectively addressed by a variant of RNN that is called long short-term memory unit. It introduced a memory state to help memorize the long-term correlation, but also has a forget gate, which will help you to focus on the short-term correlation in the data structure. And in the last several years, there's a very exciting progress in this area, which is to combine the convolutional neural network with LSTM to learn from the spatial temporal data that allow you to predict the evolution of image sequences. Right? And this model has been further extended and developed. And so there, in a more recent so-called eidetic 3D LSTM model, we use, instead of applying convolution only to space, here this model applies convolution operation to both the spatial dimension and the temporal dimension. Right? So that becomes a 3D CN with 2 dimensions that covers the space and 1 dimension covers the temporal domain. And our test shows this change, this innovation actually very significantly improves the learning capability and the prediction accuracy of the RNN model on microstructure evolution. And this is a model that we use for this particular work. Okay. So before we apply the technique to learn from microstructure evolution phenomenon, Fei first applied this technique to tackle a toy problem, which is plane wave propagation dynamics. And the reason that we like this problem is because the governing rule for this phenomenon is described by this very simple equation. Right? So it's very easy to generate ground truth and train the model and to see its efficiency. So if we use this equation to generate a number of image sequences that shows the evolution of wave propagation using different wave vector, wave frequency, and also the decay constant. And then he divide these image sequences into smaller clips of 20 frames each. And each clip serves as one data point in the training data set. And there's a total of about 1,500 clips in this training data set. So which is not really a significant amount of data. And after provide this training data to the model and the training converges, in the testing phase, Fei provided 10 input frames to the models, which shows a snippet, a short sequence of wave propagation, and then ask the model to predict how the wave should propagate in the next 50 frames. Right? And so this is the test. And the results actually is very satisfactory. So we found that when you use wave parameters such as the vectors, wave frequency, the damping coefficient, which are not included in the training data sets, the trained model is still able to accurately predict the wave propagation dynamics. Right? So in terms of the pixel-wise comparison, so we found that the root mean square error between the ground truth and the predict images is below 5% in the prediction duration. And the another measure called structure similarity index measure is above 94%. So here SSIN equal to 1 means two images are identical to each other. So the overall accuracy of the prediction made by the RNN is very nice. And so we're very excited by this this discovery, and then we further applied this technique to more realistic microstructure evolution phenomenon. So one example we look at is the grain growth kinetics. So we know the physics of grain growth is well understood. Right? It happens in polycrystal structures at a relative high temperature when the atoms are mobile, which can cause the grain boundary to move. And for two-dimensional isotropic system, the grain growth kinetics is governed by the well-known von Neumann-Mullins relations, which says the rate of area change of a grain is controlled by its number of sites n minus 6. Right? So this is also known as the n minus 6 rule. So when a grain has more than 6 sites, the grain is lucky one. It will grow at the expense of its neighbors and become larger and larger. But if a grain has fewer than 6 sites, then it will shrink and eventually disappear. Right? And we can simulate the grain growth process using a phase field model. And this is how we generate a training data set to train the RNN model for predicting the grain growth process. Right? But compared to the wave propagation example, so here we intentionally let the model subject a series of more challenging tests. And the purpose is to really better understand how well the trained RNN model is able to extrapolate what it learned from the training data set to predict unknown situation it has never seen in the training data set. And we think this is really important because it determines how much data we need to include in the training set and how efficient is the training process. And that will have a direct impact on the usefulness of the machine learning approach to microstructure evolution prediction, because we want a relative small data set, a fast training process that allows to predict a very broad circumstance of the evolution phenomenon. So here in generating training data sets, we start from a particle structure that has about 75 grains, and then we let it evolve and end the simulation at about 45 grains. So there's about 30 grains disappearing from the simulation. Right? So this is a pretty short simulation sequence. And then we convert each simulation into a 20 frame clip. And we have a total of 2,400 training clips in the training data sets. And after the the model is sufficient trained and converges, then we let the trained model to make a prediction based only on one input frame, which serves as the initial particle crystal structure configuration. And then the model needs to predict the next 200 frames on how the particle crystal evolve over time. Right? And here I want to point out that 90% of the predicted frames, that's from frame 21 to 200, they actually fall outside the time span of the training data, which is only covers the first 20 frames. Right? So the configurations in these 90% of frames have never seen by the training data set, never seen by the RNN model. Right? And so this serves as a test on the temporal extrapolation capability, up to 10 times of the training data. And the result is actually quite satisfactory. So what we found is in the short term, which is on the time scale comparable to the length of training clips, we found the prediction in ground truth has very good pixel-wise comparison. So visually, it's very difficult to distinguish between these two. Right? But when time goes on at later stage, we do notice there is some visible change, difference between these two in local regions. And this is also reflected in the pixel-wise comparison, such as RMNC and SSIM. You see the error gradually increase with the frame number. Right? But want to highlight that when you look at the statistical properties of the microstructure predicted by the RNN model, so it actually has a much better performance than the pixel-wise comparison implies. So here, for example, we look at the average grain size and also the grain size distribution. We found both of them have very good agreement between the ground truth and predictions towards the end of the simulation. And I think in some sense, this is even more important because in the end, it's the statistical properties of the microstructure rather than individual pixels that controls the performance of materials. So in that sense, I think the RNN model does a very good job in extrapolating the learning to the temporal, in the temporal domain that's well beyond the training data set. Right? In the second type of test, we challenge the model with its ability in extrapolating the learning spatially. Right? So what I mean is we initially train the model on small microstructure images of 64 by 64 pixels. And then we apply the trained model to predict the grain growth process in a larger system of 256 by 256 pixels. So that's 16 times larger in area. But we found the performance of the RNN models is as good as its prediction on the smaller domains, like both in terms of the pixel-wise comparison and also in terms of statistical properties. And that shows that, that the model is able, you don't need to train a model with very large data set for larger systems. Instead, it could be sufficient for the model to learn from a small data set in spatial dimensions, and then it's able to extrapolate the prediction to the larger system. And practically, I think this is very appealing, right? Because it greatly reduces the data amount for the training set and allows you to more efficiently train the model to make predictions. And we also did another type of extrapolation test in the configurational space. So here we let the trained RNN model to predict the evolution of some synthetic artificial polycrystal structure it has never seen in the training data set. So for example, here we have a structure with 8 grains and arranged in order fashion in the system. So this is something that's very different from the polycrystal structure in the training set, which was generated by the Voronoi tessellation that looks more like a real grain polycrystal structure. But even though the difference is very significant, the model is still able to accurately predict which grains will disappear and which grains will survive and how the grain boundary network will evolve, and has very good agreement between the prediction and the ground truth. Okay. So we're very happy with all these tests that we kind of pose to the machine learning model based on the convolution RNN, and we think it passed the test. And then we did some more digging into the data, into the performance, and we think the reason that's able to do a good job is because the RNN model can capture the evolution rules of the grain growth process. Right. So we have the following reason to support this claim, because we know the grain growth process consists of two elementary steps. So one is the continuous evolution, a continuous shrinking or expansion of a grain based on the curvature-driven grain boundary movement. Right. So here, the rate of area change of a grain is controlled by the curvature of the grain boundaries. And the grain boundary curvature is further controlled by the number of sites the grain has. And what we found is the RNN model, after training, it can accurately predict this dependence of the grain boundary movement velocity as a function of the number of sites. Right? So that captures this elementary step. And the second type of elementary steps that happens during grain growth is the topological change that happen to the grain boundary network when small grains shrink and disappear, or when two grains switch edge with each other. Right. So for a two-dimensional system, there's 4 types of topological events. So this could be the disappearance of 3-sided, 4-sided, 5-sided grains, or could be 2 neighbor grains switch edges. Right? And in each one of the cases, we found the RNN model is able to correctly predict what will happen to the local topology of the grain boundary network after these events take place. So that means the model is able to learn all these local evolution rules from the training data set. Right? So combining these 2 steps, you can reproduce the grain growth process, and we think that's the reason why the trained RNN model is capable of doing the extrapolation in to larger system, longer times, and also in some foreign microstructure that the model has never seen before. And so I feel that this actually could be evidence that the machine learning model based on convolution RNN is able to comprehend or understand the physical principles underlying the microstructure phenomenon. Right? So I know this might be a pretty bold statement, but I think mathematically what this means is with sufficient training, it is possible that the RNN can learn the mapping of the underlying structure of the partial differential equation, and therefore mimic the solutions from the time-dependent PDEs. Right? And we also applied the RNN model to study some other well-known microstructure evolution phenomena. So one is a spin nodal decomposition, which Fei presented in his talk, which is the spontaneous phase separation process in unstable solid solution systems. And traditionally, spin nodal decomposition was simulated by the Kahn-Healy equation, which is a nonlinear 4-solid equations. So here we use Kahn-Healy equation to generate simulation data, and then train the RNN model based on such data. And again, we see the model, the performance is comparable to the grain growth examples. When we use only 1 frame as the input, ask the model to predict the next 200 frames, it shows a accuracy which is comparable to grain growth, and also shows very good agreement in terms of the statistical property of the microstructure. So here in the for example, it has very good predictions on the interface curvature distribution for this biphasic spin nodal structure. And we even challenged the model with a more difficult problem, that is to predict dendrite growth, for example, during solidification process. So we know during dendrite growth, the system is intrinsically unstable. The interface between the solid and liquid phases will develop instability and generate this very intricate, complicated dendritic pattern. So here we use a simple phase field model as a proof of concept to generate the simulation data on the dendrite growth and then train the model on such data. What we found out is because the system the process is more convoluted, it does pose challenges for the RNN to make a good prediction. So for example, instead of giving only one input frame, we found we need to provide the model with 10 input frames to show a short sequence of evolution to allow the model to learn the evolution trajectory and make good predictions on the dendrite growth pattern. But the model is indeed able to capture pretty well the whole process of dendrite growth and even capture the details of the formation of the side branches and when it forms very nicely. So we demonstrate in the work that it is indeed possible to train machine learning models to learn from PD-based simulation and then replace PD-based simulations to make a prediction on microstructure evolution. But I guess the important question to answer here is why bother to do this, right? So what are the benefits of using machine learning approach to predict microstructure evolution instead of the traditional approach? And here I'd like to highlight two potential benefits. So one is was the computational efficiency. For example, in phase field simulation of microstructure evolution, it's typical that you need to resolve the interface with a sufficient number of grid points. Right? Typically, you want to have 5 grid points to resolve the interface, right? And this limits the size of system you can simulate in a phase field simulation. This constraint is no longer obeyed by machine learning accuracy, right? So for machine learning, actually, what we can do is to cross-grain the images, downsample the images, and then run the machine learning predictions on the coarser grade, and therefore be more efficient in spatial representation. And this is actually exactly what we did in the green growth prediction. So we run the phase field simulation on the 256 by 256 domain, and then downsample the data to 64 by 64 domain to represent the polycrystal structure. And then we use such downsampled data as the training data to train the RNN models, and then we make predictions. And you can see the predicted structure in this coarse grade actually has very good agreement with the phase field simulation on the finer grade. So that's one aspect of improving the computational efficiency through spatial coarsening. And another type of coarsening is a temporal stepping coarsening. So the microstructure evolution governing equations are often nonlinear high-order PDEs, for example, in phase field models. So this often place a quite, I'll say, severe limitation on the time step size you can use in a PDE solver. But when you use machine learning to make predictions, we're no longer restricted by this limitations. So we're able to use large time step size to make predictions of the next frame, how they evolve. So for the 3 examples, for example, here we used in the testing, we can use from 7 to 360 times of time step size in the RNN prediction compared to the PD solvers. And so combined with this time coarsening and spatial coarsening, we can achieve 100 to 1,000 fold acceleration when you run the RNN model on GPUs. And even when you run the model on CPUs, you can still achieve somewhere from 10 to several tens of fold of speed up compared to phase field simulations run on CPUs. Right? And in a more recent test, we even use a variable time interval schemes to allow the machine learning to make prediction at larger and larger time intervals, which is kind of similar to the adaptive time stepping in PDE solver. And this allows to further accelerate simulation, but with maintaining the accuracy in the prediction. So for example, when we start from 80 grains and let the structure coarsen until the last 5 grains, the machine learning is able to predict correctly which 5 grains will survive with 100% accuracy in our test. And And in this case, by using this variable time interval, we can further accelerate the machine learning. It can achieve more than 3,000-fold acceleration compared to the face-field simulation. And another important benefit, I think, with the machine learning prediction is that it's able to make predictions on microstructure evolution, even though even when the properties of system are not completely known. Right? So when we use PDE solver simulation to simulate microstructure evolution, we need to know all the parameters in the materials, which are captured by the equations. Otherwise, we cannot run the simulations. But in the machine learning approach, if you feed the image sequence into the model, then it's possible for the model to infer the material property from the image sequence, and then apply such knowledge to implicitly infer the material properties and predict the evolution process. So here, for example, in the dendrite growth example, we train the model with dendrite growth simulation using different latent heat parameters of the system, right? And after training, we feed the model with a sequence, with a dendrite growth sequence, which generated by a latent heat value, which the machine learning model has no knowledge about, right? So it doesn't know explicitly what is the latent heat for the imaging sequence we put into the model. But the model is able to sense this value, parameter value, from the input frames, and then correctly predict the evolution trajectory based on the input. So I think this is also very exciting, potential applications for the machine learning model. That is, well, say if you have some experimental data which shows a evolution of the some microstructure, but you do not know the entire parameter set of the system, well, then the machine learning model is actually okay. It can infer the properties from these spatial temporal data and allow it to make predictions in a correct way. Right? So let me stop here and just want to quickly wrap up and say that we have seen from our own studies, we have seen that the machine learning techniques has become sophisticated enough to allow us to learn from the traditional PD-based simulation data and then make reliable prediction on the microstructure evolution. And in potential applications, these approach can be applied to three-dimensional, can be applied to the experimental data, which is something that we're very eager to get onto. So I'll stop here and thank you for your attention. Fei and I are very happy to answer your questions.
Thank you so much, Fei and Ming, for a great presentation on machine learning for microstructure modeling and predictability. And you covered so much, and we also appreciate that you went through some examples of how this machine learning can be used. I'm looking at our members here in the audience, and I'd love for them to start preparing some questions. We encourage questions at this point, and we have enough time for a few here. It looks like we have one question queued up already. Ming or Fei? Mm-hmm.
Okay, so we have a question from Carol. So Carol asks, what are the issues that we may encounter when applying this approach to predicting three-dimensional data? So I can first take a crack on this question, and maybe Fei can complement me. So we're actually so both Fei and my students there, we're doing the extension on training the model on three-dimensional data. So one challenge we have faced is the training is definitely much slower. I guess because you have a large data sets, right? So imagine that you have more weights and biases in neural network that you need to train with, and that takes much longer to train. But in terms of the volume of the data, so actually, surprisingly, we see that actually it does not significantly increase the number of training data set that you need to allow the model to converge. And another potential challenge is that in 3D, because it contains a very large memory, and these machine learning models, they are memory hungry. And so that limits the size of the three-dimensional data you can go. So for example, right now we're training the model on 32 cube mesh, and we found if you want to go for 64, that imposes a very significant burden on the memory of the of your clusters, and that's something that that also will could limit the applications to the three-dimensional microstructure prediction.
You have two more questions?
I agree. So just to the previous question, yeah. So in principle, there is nothing that stops us from going to 3D, even though there are some technical challenges like managing the memory constraint, because usually you run those training on GPUs, and GPUs tend to have a limited amount of RAM. But we can, we are working to get around those, and we were able to get fairly decent results in 3D.
Yep. So Fei, do you want to answer Ming's question?
Okay, so Vince is asking how generalizable are the trained model so that training time can be offset with reuse. Okay. Okay, yeah. So good question. So one of the things that we discovered, like Ming hinted, was that we can accommodate a fair amount of variety in the parameters, right? So one way of thinking of this is that you can train a certain mechanism, certain physical mechanism with different parameters like the latent heat, and once it is trained, the model can accommodate different parameters and become very reusable. And another way, which is still a work in progress, is to supply both the trajectory and the parameters that you use to generate this trajectory into the training process, so that when you reuse your model, you can specify the parameters and get fairly accurate results. So those are sort of a couple of thoughts on how to increase the reusability of the trained model.
Right, I agree with Fei. And Ming also has a question on, can we invert the example from the last slide? That is, to given an image sequence, can we infer the underlying parameter from the image sequences? And the answer is definitely yes. Actually, that's something we're working on. So we already showed that it's possible by adding a regression layer, combine the regression layer with the RNN model, that you can infer the regress the parameters from the image sequences. It actually works pretty nicely for the plane wave propagation examples, and so we're trying to test on the other examples. So I think this is also related to the question from Carol, asking about, can we use this approach to tackle with anisotropic properties of the system? And that's also exactly what we will hope to tackle with. So for example, with anisotropic green boundary energy and the green boundary mobility, and that will lead to different green growth behavior. So the hope is, if you have a data sequence that shows how the green boundary structure evolved over time, can you infer the green boundary energy anisotropy and mobility anisotropy from such image spatial temporal data? And I think it's in principle it is possible. So we're trying to do a proof of concept demonstration on that using the green growth as one example.
Okay, Ming and Fei, I want to thank you again for such a great presentation. And I know that people will want to ask you questions continuing on in the next couple of weeks, I'm sure. I want to thank our audience again for attending. We have a recording available next week. And also we welcome any future webinar topics. Also, we look forward to seeing you on May 12th for the intersection between a CO2 economy and critical materials, Los Alamos R&D portfolio and critical materials by George Guthrie. We look forward to seeing you again in 1 month. Thank you all for joining us. And thank you, Ming and Fei, for a great presentation.
Thank you.
Thank you.